Let me thank the organizers for giving me an opportunity to share some of our research findings with the audience of the World Nano 2022. So whenever we plan a complicated manufacturing process, it is not possible to do everything theoretically. A new phenomena which had to be experimentally verified. As you know, the number of process parameters are increasing. Conducting the test also will be tedious. So we have to plan a proper design of experimentation so that whatever result we are going to expect, that we have to get it with less number of experiments so that we can minimize the cost, experimental time, as well as the desired result. In this respect, the nano powder, which is being used in the manufacturing to safeguard the tools.
No, doctor, sorry to interrupt you. Sorry to interrupt you. Your slides are not moving forward.
Yeah, okay. Front. Yeah. So one of the manufacturing process, the electrical discharge machining. It is a thermoelectric process, formation of the plasma channel between the tool and the workpiece. This type of process will be useful for machining of super tough electrically conducting materials. As you know, Inconel 800, that is iron nickel chromium alloy, is extensively being used in nuclear reactors, chemical vessels, and electric power plant equipment and equipment in petrochemical industry. So to have a good finished product, the machining process, electrical discharge machining process, two types are there. One is die sinking electrical discharge machining, EDM. The another one
put
is
the presentation in mode presentation.
Wire cut EDM. Other types of EDM to improve the material removal rate and surface finish. Vibratory based EDM is there, water EDM, dry EDM, and powder mixed EDM. Here, the nano powder is helping a lot to safeguard the tool as well as the realizing a good product. So my present interest is how the nano powder is mixed and it is useful, and how to develop the process parameters optimum to realize a good product and improve the material removal rate. These are the things what process designer is expecting. So there are major references for my work. One is Taguchi technique for quality engineering. It is a very famous reference. Any new phenomena you are conducting the experiment with a number of parameters and number of levels, you can plan the design of experiment with a few experiments and how to get the complete information from a few experiments is explained in this Ross book. Then regarding the nano powder mixed with the thing, the electrodes and coated electrodes, good experimental details are available in the second reference by Karnakaran and Chandrasekharan. And majority of the people who have used this Taguchi technique, they have not followed the full potential of this technique. So how to make use of the technique, what are the benefits, everything is explained in the third reference. So outline of my presentation, it is mainly focused on the machining of Inconel 800 in powder mixed electrical discharge machine, electrolyte, copper electrode, as well as silver coated electrolyte copper electrode. The basic idea is which will give good performance and good realization of the product made of Inconel 800, and at the same time, what are the process parameters are involved with less number of experiments. That is what I am going to present. So in this experiment, three different independent variables are there. They are current, peak current, gap current, pulse on time, and pulse of time are the process parameters. Material removal rate and surface roughness, as well as tool wear rating, are three dependent performance indicators. So modified Taguchi approach we have followed to conduct a few experiments, generate the performance indicators, and afterwards find out the full factorial design and confirm with the test result, so that next time, after getting the confidence about the method, there is no need to go for full factorial design of experiment. With less experiments, we are in a position to find out the optimum process parameters. Finally, the empirical relations for complicated experiments, the performance indicators in terms of process variables we have developed in a simple way. No software is required. With the Excel sheet, on Excel sheet itself, we can find out. So the first thing is test data is required to validate any method. So the Karunakaran and Chandrasekharan have conducted the experiments. Then low viscosity kerosene as the dielectric fluid. They have used aluminum powder is mixed with the kerosene and stirred in magnetic stirrer for nearly 9 hours to minimize the size of the particle to 5 nanometers. So aluminum nano powder concentration is 3 grams per liter. The workpiece 22 mm dia and 20 mm length, whereas the copper electrode is 25 mm dia and 23 mm length. These are the sizes they have used. The machining time for each test run they have done for 5 minutes. So as usual, the material removal rate and surface roughness they have measured. The low surface roughness will give us the good quality, means surface finish will be very good. And the material removal rate, the manufacturer will expect the more material removal rate means he can realize the product earlier. These are the two constraints on the output performances. Now, how it is possible to develop the Taguchi design? Taguchi design of a approach, suppose number of process variables are NP and the correcting levels are NL. So number of experiments required as for the Taguchi is 1 plus NP times NL minus 1. For example, in the present case, the process variables are 3. And the levels also assigned as 3. So when I substitute 3 into 3 minus 1, 3 into 6 plus 1, 7 experiments are sufficient. So Taguchi has suggested the L9 orthogonal array. L9 orthogonal array, that means we have to conduct 9 experiments as for this. So the measuring parameters are peak current, pulse on time, pulse of time in microseconds, current is in amperes. We are, for simplicity, we are designated by the symbols ABC. So 3 levels are fixed for peak current. 5, 15, 20, average is 10. 6, 8, 14, average 7. So generally in engineering point of view, lower value of the parameter, higher value of the parameter, and average. Then the performance indicators we have put, this is material removal rate, grams per minute, surface roughness in micrometers. Surface roughness should be minimum, material removal rate is maximum, that is for the optimization technique. So from these levels, we will be finding what are the ANOVA, analysis of variation. So material removal rate, first mean, second mean, third mean, and their percentage of contribution on the average value is estimated. By knowing this, we can find out optimum. For example, in material removal rate, you wanted to find out the maximum value. See from the first, second, third mean, which is the maximum. So the third mean is the maximum. So for the parameter A, level 3 is maximum. That is why A3. Similarly, B also B3 is coming. C also C3 is coming. D, it is coming as D2. Second one is the maximum. So if you consider these parameters, you can achieve the maximum material removal rate. Same way, maximum surface roughness also you can find out. Minimum surface roughness means you have to see the minimum values. This way, it is possible to find out the optimum values. So from these mean values, it is possible to estimate whatever combination of the parameters are there by taking the respective mean values and the grand mean. So using this, this is called additive law, well described by the Ross book, and many of the papers it is described. Then we have used this fellow, and estimated. You can see this is the test result. This is only 3 process parameters we have considered. The relative error between the test and estimate is below 7%. Suppose if you are considering the error term also into the consideration of the D parameter, exact result is coming. So from this, what happens, we can find out the estimated range from minimum to maximum. So whatever we have estimated, all the test data is falling within this range. Then by changing the levels of the parameter, we will be in a position to find out the 27, all possible things we will be able to find out. Now, the 27 data points, when you are seeing the material removal rate test and material removal rate estimate, the lower bound and upper bound, the exact 45-degree line is passing through middle of them. Only few of them are very close to that test data. Similarly, for the surface roughness also, we have estimated the lower bound and estimated upper bound. All those things, the test data is falling between lower and upper bound. Only few data points are close to that. This clearly confirms that there is no necessity to go for complete full factorial design of experiment. We will do few things as suggested by the Taguchi design of experiment, and we can get the complete information. Afterwards, how to develop the empirical relation. From the mean values only, we have developed the empirical relation. From the mean values only, we have put the bounds, means the correction factors to get the lower and upper bound values. If you substitute this, the intermediate values in the levels also we can find out. That is the added advantage of going for the empirical relations. Now, when you are doing earlier one without coating, silver coating, the copper electrodes were used. Now, what is the advantage of going for silver coating with the copper electrode? Same experiment with the same levels were repeated. But what we have done, just like nanofluids, how much percentage enhancement is there by adding the nanoparticles to the base fluid? So we are taking the ratio, all the fluid properties with respect to the base fluid. So here the base I am assuming without coating, uncoated, and coated copper electrodes I have taken. The factors I have arrived, MRR coated by MRR uncoated, surface roughness coated by surface roughness uncoated, so that once these factors are available from the previous experiment itself with these factors, we can find out what could be the range impact of a coated copper electrodes on the performance indicators. So we are able to find out the empirical relation similarly what we have done earlier. And from that empirical relation and the previously uncoated one, we have developed the empirical relations for coated one. Then if you see the next few graphs, Here also they have conducted the experiments. The complete experimental data versus the lower bound and upper bound, the experimental data is in between or close to the lower and upper bound predictions. So this is the surface roughness for the coated electrodes. Now the next question is optimization. You are having maximum material removal rate and minimum surface roughness. When you go for the maximum material removal rate, whatever set of parameters you are identifying, they may not be same to give the minimum. Since these two objectives have different sets of optimum parameters, we are forced to go for multi-objective to get a set of parameters at which the possible maximum material removal rate and the possible minimum surface roughness can be achieved. So this is what a new type of thing we have introduced by introducing a weighing functions and a normalizing. Because material removal rate is one property, surface roughness is another property, you cannot add or subtract. So after normalization only it is possible to do it. So we have done the normalization and did the job. So on Excel sheet itself, these are the variables. First one is material removal rate. Second one is the surface roughness. After normalizing, we are getting these things. Then the evaluation, final value of this, same analysis of variance we have found. Finally, the minimum value is coming A3, third level for A, third level for B, and the first level for C parameter. So this is the optimum parameter at which you can find the maximum possible material removal rate and minimum surface roughness. So this is not only for manufacturing, any other complex phenomena where a lot of parameters are there, you can conduct the experiment. So when you see the copper electrode and the coated copper electrode, optimal process parameter peak current is 15 amperes, pulse on time is 8 microseconds, and pulse of time is 3 microseconds. The MRR estimate is this range, whereas the test result is surface roughness estimation is this, whereas test result is this. So when you go for the coated, from the factors arrived, we are able to get 0.78 to 0.89 grams per minute, whereas test result is 0.79, that is in between. SR estimate is 1.57 to 1.68. So test data is 1.64. So these are all falling within this range. This confirms the validity of multi-objective optimization. So when I come back to the conclusions, we have specified optimal nano particle mixed EDM process parameters for Inconel 800 to achieve maximum material removal rate and minimum surface roughness. Assess the significance of the peak current, pulse on time, and pulse of time by performing analysis of variance. Test results are within or close to the expected range of MRR and SR. Little improvement in MRR is noticed with coated electrodes. Modified Taguchi approach, whatever I have explained, it provides the expected range of performance responses. As you know, when you repeat the experiment, you will not get the same number. There will be some variation that we can capture. Then, functionally, the dissimilar quality characteristics of multiple responses represented by a single response characteristic for optimum solution following the Taguchi approach. So these are my concluding remarks. The method of approach, whatever I have explained here, are shown in my published papers that will be very useful, not only for manufacturing problems, for any new experiments where a lot of parameters are there and you are setting the levels, it is possible to find out the optimum solution and complete information accurately. So, are there any questions from the audience side? I will answer.